Good day. This is going to be part 5 of the 7-part series for the Chapter 2 lecture series. We're going to talk a little bit about material properties versus temperature, the differences between compression and tensile testing, disk testing of brittle materials, torsion testing, also known as shear testing. It's a way to determine shear. And a little bit about Poisson's ratio. You're going to see a lot more of that in your future classes. And then we're going to finish off this short lecture with the basics and concepts of bend testing. So think about this. If you have a material and you increase its temperature, what do you think the material properties will look like? The ones that we've talked about so far in this lecture series. So, what does elongation look like? What about tensile strength, yield strength, elastic module? So the elastic modulus. What happens to that is you heat up a ductile metal, for example. So, if you think about it and go back to the case of like taffy, right? We played with taffy before. It's kind of a fun material. If you warm it up, it's easier to pull, right? So oftentimes when they make taffy, you see it's warmed up. They pull the taffy and they create all the different candies out of it. So you can also do the analogy that if you heat up metal, it gets easier to pull on. It stretches easier. We call that ductility. So the ductility actually increases, right? We can elongate the material a lot easier for the same forces. So this is a great graphic to take a look at and be familiar with. On the y-axis, you see the stress, okay? And on the x-axis, you see temperature. And you can either use the SI units of megapascals and Celsius, or you can use Fahrenheit, okay? And we also have a little bit there on the elastic modulus in gigapascals and the elongation. So if we take a look, right, yield strength, tensile strength, okay, these two, which axis would they belong to? Okay, well, that would belong to the left axis, the stress in megapascals. Okay, so let me get my magic pen. Okay, so this graphic goes with the stress measurements on the left side. Now the elastic modulus goes with this scale on the right side. So you can see as the temperature increases, okay, either in Fahrenheit or in Celsius, right, as it goes up, the elastic modulus decreases. And you kind of expect that. Things gets a little stretchier. It's easier to stretch. Remember, the elastic modulus is in the elastic region of your stress-strain curve, okay? It's the linear part. It's the part that, we get Hooke's law from. And so in that area, the elastic modulus actually decreases with increasing temperature. And you can kind of visualize that, okay? And then, of course, the tensile strength would also go down as you increase temperature because it's easier to pull on the material, okay? And then the yield strength also decreases. That's the end of the elastic region, okay? So and also the elongation, it stretches a lot easier, okay? The elongation goes up for a given stress, so the elongation, which is related to strain, of course, how much you've stretched it by, increases with increasing temperature. And this all makes sense. So if I were to give you a graphic like this on your exam, and then you had to maybe match, which is which, right? You would be able to do that. And it is important. You might say, well, tensile strength and yield strength, I don't know which way it goes. Tensile strength is, if you remember the stress-strain curve, it's more or less linear, and then it goes into the plastic region and then comes down and breaks. Okay, the tensile strength is up here. The ultimate tensile strength is at the peak. Okay, where it starts to yield is where it goes from being a straight line to not being a straight line. That's going to be less. So the yield strength is lower than the tensile strength. So I want you to study this graphic and really understand it. Okay, I could see this on an exam. All right, so we did tensile testing where we pulled, right, on our sample and stretched it. But what happens if we push down on the sample? Okay, so this image here is taken at 4 different times during a compression test. So this is before compression, so it's a nice cylinder before we apply any kind of compressive load. Okay, and then at some time later we've applied some load. Okay, now my cylinder is starting to bulge a little bit, right? So you kind of expect that. Let's see if I can visualize it. And then after some time and more load, we get this nice barrel effect. Okay, and that's for compressive testing. So this is a really good example of, you know, different kinds of testing you can do to get different information. So it's called barreling when it starts to bulge out. And you know, that happens because you've got frictional forces along the platen that's trying to keep that radius, that diameter, the same. Right? Think about it. As I'm pushing down, it's going to want to spread out, right? The platen here that's pushing on this thing. Ugh, my drawing is terrible. Right? There's this platen, this flat plate that's pushing down on your cylinder. Well, you have forces in there. Let me get another color. We'll do blue. So as you're pushing down, right, with the platen, there's frictional forces opposing the expansion at this point, at this plane here, right? So we've got forces pushing in. Okay, and that tries to keep the top and bottom of the cylinder in the same shape as when it started. So now you're going to get all of these shear stresses, right? Lateral stresses, trying to, you know, push the material out. So you don't have those frictional forces inside the cylinder. You only have it on the boundary conditions, on the edges, on the top and bottom. So the result is you start to get this barreling effect. Now, to reduce the barreling effect, you can reduce the friction. Okay? And reducing the friction, you can add lubrication. Okay? So lubricating the platens will improve the test, right? You'll have more of the forces going into the lateral expansion of the material, and you'll get a better stress-strain curve for compression. If you do it right, your stress-strain curve for compression will be able to be overlapped with your tensile stress-strain curve. Okay, and they'll overlap each other really well. If you don't have lubrication, then those two curves won't overlap very well. Okay, so these tests are usually harder to do, and it's only done if, you know, the design that you're working on, it's important to really understand the compressive forces and what they do to the material. All right. All right, so if you have a good test, the tensile and compression curves are going to overlap for ductile materials. These are like typical metals. Brittle materials, brittle metals, not so much. Okay, so brittle materials tend to be stronger and more ductile in compression tests as opposed to tension. If I pull on a brittle material, it snaps. If I push on it, it will compress a little bit and it'll be stronger. So, you know, you're going to choose different materials for different applications. Okay, so in the typical compression tests, right, the cross-sectional area varies across the sample, and this makes it tough to define the stress-strain curves. Okay, because, you know, remember when we were doing tensile testing and we were pulling in the elastic region, that cross-sectional area got smaller, but it's got smaller by the same amount along the whole test sample. Now if I'm compressing it and it starts to barrel, then that cross-sectional area isn't constant in the lateral direction. So you have changing cross-sectional area, but you have area changing as a function of the Z direction because of the barreling. So the cross-sectional area here is different than the cross-sectional area here. Okay, now if you lubricate it, it'll stay more or less constant. Okay, so think about that a little bit. We talked about brittle materials. So typically what we do when we want to test brittle materials and their and get their stress strain curves for that and find out, we usually try to find out when it fractures, right, when it breaks. We will make a disc like the picture shown over on the right. So this disc has a certain thickness right here, T, and a certain diameter. So here you see D, okay, and then here you see thickness. So this is the diameter, D, and this is the thickness, T. And the force applied is actually 2P because you're pushing on it, but it's also pushing up on it. Okay? So you've got twice the force divided by the area. And you might say, well, how is this an area? Well, it's the area, it's the cross-sectional area. This times the distance, right? So it's thickness times the diameter. So you can take a look at it and kind of think about it. If I make the diameter bigger, the tensile strength, this is the point, the strain, or it's the stress when it breaks is called the tensile strength. Okay, so that's when the force is at a certain point where it breaks. Okay, the applied load, and you can think about it. If I make it thicker, okay, it's going to be harder to break, right? So I'm going to have to put more pressure on it. And if I make it bigger, the same thing will happen. Okay? So, you know, this is just another kind of test. You know, the more common one, of course, is the one we talked about, the tensile testing. But there's a nice page on this in the book, so go ahead and read through that as well. And the other thing to think about is why do you think the fracture is vertical on this thing, or in the direction of the force? Well, if you think about it, if it was a ring, it's going to try to squish it, right, and make it oval. It'll try to make it oval when you push on it. So the forces inside are going to go laterally, going to go towards the outside. They actually use these things to make pipes. It's kind of interesting. If you get a piece of metal and you push on it, you're going to create an opening in there, and you can make a seamless pipe if you do it right. All right, so we talked about stress strain curves, right? When you pull on something. But if you shear something, right, you maybe fix, let's draw another version of a shear test before we talk about this radial one. If you have a block, okay, and you fix the block on the bottom, hopefully you can see this. Okay, so this surface doesn't move. I glued it to the table. And then I pull on the top of this, okay, with some force or some load, right? And if I pull on it hard enough, it's going to kind of look like this when you're done. So let me change the color of that. Right? You're going to end up with something that looks like this in the end when you pull on it, and you've distorted it by this angle. So you have an angle change from orthogonal. You have this delta angle here, okay, due to the shear forces. And when you do that, you can calculate the shear strain. Okay, and the shear stress. The shear stress has to do with the force you put on it, the distance, this is, right, and the angle this force is relative to the surface. Okay, so an easier way to do this kind of test is to do a twisting test. So you get your pipe, right, the cross section here is a pipe. That's a really bad color with a white background, so let's go to laser pointer. So you have a pipe, right? That's what it is. Then if you look at it from one side, right, it's a pipe, and then you're going to twist it. So usually they make it where this is a little bit smaller here. It's kind of like the dog bone design for the tensile testing. And you're going to grab each end of the pipe, and then you have a machine that's going to twist. Okay? And it's going to shear in the smaller diameter area. The rest of the pipe isn't going to shear much because the forces are higher in this region here across L. Okay? So you can imagine when I twist something, it's moved a little bit. So how far did it move? Well, you take the radius and you multiply by the angle that it's twisted, right? So that's r theta. Okay, and then it's done this over a distance L. Okay, so your shear stress is related to the torque, the average radius, and the thickness of the tube, okay, at the narrow section. So that's how thick the tube is. So you think about it, I'm applying a force, which is a torque. It's a twisting force. And I'm doing it over the area that's r squared t. Okay? So that gives me this area here pretty much. Okay? So, and that's defined as the shear stress. So that's pretty straightforward, and it directly correlates to the XY version of it. Right here we're in rotational coordinates. Here we're in Cartesian coordinates on the upper right. Okay, so what is T? Well, T is torque. Right? Remember twisting force. We learned that in physics. Okay, and then this is a little review from physics. So torque is R cross F. Right, it's a cross product of two vectors, and it's a number. And R cross F is equal to RF sine theta, where theta is the angle between the R vector and the force vector, which is usually 90 degrees. So the sine of 90 degrees is 1. Okay, so now you can see in the numerator you have RF. Okay, torque is RF, assuming that the that the angle between the force vector and the radial vector is 90 degrees. So if you look at T in the numerator here, say, okay, that's RF, then you're going to get F over RT. And RT is dimension units, right? So you've got force over area again. So shear stress has the same units as engineering stress or true stress, right? It's force over area. Pretty cool. Okay. So the shear stress tau is equal to the torque divided by 2 pi r squared t. So what are the units? And I just mentioned them, right? They're the same as what it was for engineering stress and true stress. So I'll let you think about it. What are the units? It's a pressure unit, which would be pounds per square inch, or megapascals, which are newtons per meter squared, that sort of thing. Okay? So this is just a reminder in this slide that torque is in the units of force and distance. The denominator is in the units of volume. You take the ratio, right? Meters cancel out, and then you get force over pressure. All right. So that's the force that we apply to twisting it, right? Now we're going to see how far did we twist it, and we already mentioned that. That's the shear strain. So it's R theta L. So R is the radius of the pipe. Theta is how much I've rotated it by. And L is over what longitudinal distance did I apply that strain to. Okay, so you can imagine if L is bigger, you'll need more force to turn it the same amount. If it's very thin, it'll be easy to twist. Okay, so what does it look like? Well, it's a unitless number again, R over L, right? And this is in radians. Okay, so it doesn't have physical units. Okay, and then try to remember what the engineering strain looked like. Well, that was L minus L naught over L naught, or the natural log of L over L naught if it's the true strain. Okay, so you get a good idea. And I added this video in. This is a nice YouTube video which talks about shear strain, but from the rectangular coordinate perspective. Okay, so you should watch that as well, and you'll be able to compare the two. Okay, so again, angle of twist is how far I twisted it times the radius, right? So the more I twist it, that bigger the angle of twist is. And then this is the linear distance, and I have it down in the bottom corner here. The linear distance along the axis of the pipe, okay, the longitudinal axis of the pipe, okay, and it looks a lot like the engineering strain, okay, in terms of units. All right, so let's backtrack to the modulus of elasticity. That was in the linear region of the stress-strain curve. And it's the stress divided by the strain, rise over run, in the linear region. So we have a similar relationship for shear modulus. Okay? So the shear modulus of elasticity we call G instead of E, right, is related to the elastic modulus. And you'd expect that, right? The stretchiness in the X or in the Z direction is going to be related to how much lateral forces that in the perpendicular direction you need to shear the material. So first of all, G, okay, which is the shear modulus of elasticity, is just the shear strain or stress, shear stress, tau, divided by the shear strain. The shear strain is R theta over L, or R phi over L. Is that a theta or a phi? That's a phi. Okay, but it's the angle of twist times r divided by the longitudinal distance over which you're shearing. Okay, so that's in the denominator, and then this is the shear stress in the numerator. And remember, that was torque over 2 pi r squared T. Okay? So if you take those ratios, you can show that's related to the elastic modulus, because the Poisson's ratio relates the longitudinal strain to the lateral strain. The lateral strain is related to the shear strain. Okay, so these two, the shear modulus of elasticity and the elastic modulus, right? In the elastic, you got to stay in the elastic region of the material. They're related to each other, as you'd expect, and so they've come up with this number called Poisson's ratio. Okay, so these are material properties, aren't they? Okay, they're ratios. So it's not about geometry, it's about the material, and that's why we do material testing, to come up with the material processing. So here's a quick snapshot of what Poisson's ratio is. The definition is lateral strain divided by linear strain. Okay, so the linear strain is along the cylinder, up and down in this case, and the lateral strain is going out. So how much does it, or going in, how much does it change dimensions in the z direction, and how much does it change directions in the x direction, or the radial direction? And that gives you Poisson's ratio. So you can do a test, you can measure the diameter before and after the test, as long as you stay in the elastic region, and you look at the change in length, okay, and you get Poisson's ratio. And that's a material property as well. So you've got the elastic coefficient, right, the elastic modulus, and then you have the shear modulus, and they're related to each other through Poisson's ratio. So, you probably want to sketch this out and think about it and draw some pictures. And these are some good videos here, okay, that you should watch about Poisson's ratio. And I think this is the last part of the lecture. We're going to talk about bend testing. So we can pull on things, we can push on things. We can do the disc test. We can do the compression test and the tensile test, and now we have a bending test. And there's two basic kinds that people typically do. There's the 3-point and the 4-point test. And the bending moment, that means where the forces are. You can see it increases, and then it's constant, and then the moment is in the opposite direction. So it's bending down in two different directions. Okay, that's what the bending moment is. Okay, and this is a really cool video on doing a bend test on the iPhone, right? That used to be a big deal. People would take their iPhones, put them in their back pocket, and sit down. And there's a hell of a lot of stress on that iPhone. And in the old days, the glue would start to separate, and then the iPhone wouldn't be as waterproof. And occasionally the screen would break. And of course, iPhone, Apple, also Samsung, LG, the phone companies have made their cases stiffer and less prone to bending. Okay, so the shear stresses have to be much higher to cause it to bend and to break. So I encourage you to watch that video. It's kind of fun. So think about a bend test. What's going on in a bending test? Can you draw the compressive and tensile forces that are in there? So if you think about it, this thing is going to bend, right? It's going to bend down. Okay, so one side of this plank is going to want to pull apart, and the other side is going to want to push together. Okay, So these are the arrows here. Let me get my pen out. So you can see as I push down on this thing, this surface here is going to want to bend. Okay, so it's getting longer. Let me, all right, so you get this nice curve going. So this bottom part of the plank is trying to get longer. So it's like it's under tensile testing. It's being pulled apart. But likewise, this is getting shorter relative to the other side. So the forces on the top are pushing in. So that's like a compression test. Okay, so bending tests kind of combine compression with tensile testing. And it's a really good test to do, especially if you're going to make shelves or balconies or things like that, right? Where you're going to have a force on top pushing it down and the whole thing's going to bend. And this is like for bridges, okay? So you're going to have these forces going up and down. All right, so that's the end of part 5. Go ahead and have some coffee before you start in part 6. And at least this semester, you're going to have a quiz after each part. I'm probably going to continue that on in future semesters. So, you know, if you're not in the fall of 2020, you probably will get a quiz as well after each part. All right, take care, and hopefully you're all doing well, and stay safe. Wear your masks.